Okay, thank you for all. My name is Marcelo De Cicco. I'm from Brazil, and I work with Meteors since 2015, coordinating the Ixos project Meteors in Brazil. And I've been making a study with Iharka from Cluj-Napoca Observatory in Romania. And today I'm going to talk about grazing meteors, how grazing meteors can help LEO satellite orbits evaluation. Well, first of all, I'm going to talk about a little about the how to make calculations when you are studying grazing meteors, because we have close encounters issues about grazing meteors. So our motivation is how does an Earth grazing meteoroid graze one more time the Earth? Can we make predictions about how many times he will have approached Earth until collide, if it will? And the pass using a kind of a backward symplectic integrator. And can we predict if it had a close encounter with Earth? And about the LEO satellite orbit, can we have a better accurate forecast using this grazing meteor studies using the symplectic integrators? Because for directing, guidance, navigations, we need an adequate integrator and, of course, a more precise solutions that are needed. So we published this year a paper about studying grazing meteors, where we showed this symplectic integrators approach. Well, so what is a grazing meteor? Well, everybody here knows that it's a meteor that can penetrate the atmosphere in a near horizontal path and a perigee very high to the ground. And generally, only a part of their material is ablated during this air interaction. Well, what is happening at close encounters? Well, the equation of motion shows singularities. When the distance between the bodies approach zero, that it's close encounter, then the forces acting between particles approach infinity. And this event produces sharp bends of the orbit. So the numerical precision after the collision will be worse because of the round-off and truncation errors of this computation. And the close encounters, where not actually singularities occur. We can use time step control, decreasing the size of the time steps. The numerous small time step will introduce numerical errors. In contrast, all solutions can be determined analytically or numerically if the singularities are eliminated. This is called regularization method. The removal of the singularity from the Newtonian does not necessarily imply the absence of singular terms in the equation of the motion. The removal of this singularity, so the continuation of the orbit of close encounters, that it's a kind of collision, it's not feasible, since the solution encounters the singularity can present a problem. So we started with numerical integration using a symplectic fourth order procedure, that it's a numerical integrator that its scheme is for a Newtonian system. To remember, a Newtonian system, it's a dynamical system characterized by a scalar function known as Hamiltonians. Okay, so I'm going not to talk so precise about this, all of these calculations. So the numerical algorithms, because the large separation of time scales involved from a day to billion of years, we need the specialized integrated to predict the optimal evolutions of planetary system over the entire lifetime that can correspond to up to 10 to 12 orbits. About the evolution of dynamic system, in this case for many planetary systems, including the solar system, higher order method that offers better accuracy at a fixed time step. So we use a Wisdom-Holman integrator, that it's a kind of a symplectic integrator. Let's move. So this is just showing how do you use for our first approach, use this for ordinary symplectic integrator using the coefficient, four coefficients. Then we move forward to a better and more sophisticated approach using 9 stages. That it's a little more complicated. Note that the schemes of or the 6 or higher, this require more stage than composition, and on only the 4th order methods, it seems more promising, including additional stages that are more efficient methods that can be obtained. So we are studying using a circular and elliptic approach. The circular approach is also known as CR3BP, circular restricted three-body problem, that describes motion of a spacecraft, for example, or a meteor, under the gravitational attraction of two massive bodies. And then we can make using these particles, they revolve around a barycenter and in a rotation frame that are fixed in this barycenter. As well, we have this elliptic approach that it's the difference that we now are considering as elliptical orbit of around the barycenter. Okay, so I'm showing the structure. How do you do the calculations using the first approach, the circular, that we are now making tests, and then we are moving for a better approach that it's this elliptical restricted three-body problem. Okay, that it's more sophisticated and it's more precise as well. So we need to remove the singularities because the numerical difficulties associated with integrations of these closed two-body boundaries, we can avoid introducing, we call that it's called regularizing transformation that remove the singularity. It was proposed by Euler and studying rectilinear motion, and the definition of regularization is as the elimination of singularities occurring in the equation of the motion. So I'm just showing how we can remove these singularities, that is 1 per pair. So you make a substitution, and now you consider time as an independent variable. And it is this 1 per pair, it's substituted by this S, letter S. More example about how to do this conversion making the time dependencies variable. You can use the Cowell method as well, the Sandman, where you do the rule of chain using these derivatives, and you can change the variable. So you not you avoid now the singularities 1 per air, for example, in the equation of movement. Now, about the regularization methods that you are applying in the study of the motion of celestial bodies, it shows that it's more efficient. We avoid the singularities. Let's say 1 per 0 example, when the air that it's a distance, it's approaching to 0, so you can have singularities. And you use some regularization methods to compensate the infinite increase of the velocity at collision, and use, as I said, a new independent variable, that it's a kind of fiction time. So the equation of motion are regularized when you do two transformations, the time transformation and the coordinate transformation. So I think it's good to note that the most important part of the regularization is the time transformation. Now I'm showing some equations. How do you do this regularization in this using in the problem of three body in a circular case, and you can then use this method to avoid things as 1 per 0 problem. Sorry. Then you have also the same approach now using the elliptical approach that it's more complicated. Now we are, our team, me and Iharka, we are now making tests and improving for use this approach in our next works. Okay, so how could you use the grazing and correlate this with LEO orbits? Well, first of all, we study a grazing fireball that happened in Europe in 1999. It was a very famous grazing, and it was published in 2 articles with Ceplecha and Borovicka, and I'm showing just the images of this big grazing fireball, and it was caught by 3 independent observations in Czechoslovakia in the European Fireball Network, and it was a big grazing. It more or less 44 kilos, and it lost about 0.35 kilos. It seems that it was type 1, a stony meteoroid. Well, then we got this orbits elements that were published in the Borovicka and Ceplecha work, and then we try in our narrow integrator that we are now studying, and then now I'm just showing the before and after these close encounters, that using just the elements of the article. You can see that the semi-axis shrank more than 10%, and you can see in the right image the before and after orbit. Well, in order to begin our study, we for comparison, we started to use the Rebound package for integrations. That it's an open source software, and we did some tests, and I published in 2020 a small article in Meteor News using Rebound, studying a very long meteor, and I'm presenting just some results, and it was a very nice calculations. Well, so using the Rebound, we apply into our grazing meteor using the orbital elements from the Borovicka and Ceplecha article, and these are the results showing the graph of the orbits, very similar to that one that I showed in the slides before. This is using the Rebound package, and more. We did more calculations. How many minutes?
4 more minutes.
Okay, thank you. So using this integrator, we use as a to compare those results with the nearhorizontal integrator that I'm going to show you now. These small results, you can see the variation of semi-major axis using Rebound package after and before the closing contours, and then using now let's move to the numerical integration using this symplectic order called nearest integrator. You can see the format of the orbit, the shape. It's very similar to Rebound that we showed before, and this upper view and side view of this orbit, we do backwards and forwards for 1,000 years, and it was a very nice result. Now we are adapting this symplectic nerve integrator with the circular and elliptical regularization method. So some conclusions about upgrades: that we need to improve the velocity, to a better orbit calculation model, and we're proposing this Newtonian approach using circular and elliptical restrict free body problem, and applying some regularization methods. So we had in Brazil a fireball case that people confuse this one with a satellite re-entry with a fireball that was very known in my country, and it created a debate about this. And unfortunately, I don't know why the video of this is not working. Sorry. So it was just to show you how these cases of grazing and entries are so important to study. Okay, so then Cipher company, it's a company that studies track satellites. They make some calculations, and it was really a satellite entry. So we need more efficient techniques to study satellites' orbits, and you can use these results that we are studying from a new approach of integrations, because thousands of satellites are orbit the Earth. So for the analysis of the satellite mission and design its trajectory, as well as for directing, guidance, and navigation of artificial satellites, it's necessary to be able to calculate the most accurate forecast. So a precise orbit prediction of the artificial satellite's motions depends, of course, the correct initial conditions. So the analytical and numerical part of that we are doing and study present a more efficient technique that emphasize with a concrete application of new satellites. So, using the close encounters approach, Iharka did some studies with using some transformation methods for regularization called ES, using initial conditions, then the method that it's just show you, and then applied to then it was applied to a object CZ5b that he entered in November 2022, and using the calculations, it was very similar to the sites that make tracks of satellites, and those are the results of the calculations. The orbit observed was calculation using the ES transformation and those numerical methods. In the table, you can see change of some orbital elements of the rocket body before entering. So the orbits became circular, its mean motion almost doubled, and the period of revolution decreased, visible in its last 5 days. So thank you for attention, and I would like to thank everybody to hear my presentation. Thank you.
Thank you.